Welcome to this presentation on declarative versus imperative languages, where we will explore two fundamental programming paradigms. In this presentation, we will go through key concepts, differences, and examples to understand when and why each paradigm is used. Let's begin with a quick overview of what we will be covering. Our objective today is to understand the differences between declarative and imperative programming. We will also explore real-world examples and use cases for each paradigm to help you understand how they shape the way we write code. Imperative programming focuses on how a task is performed using a sequence of statements. In this paradigm, you tell the computer exactly what steps to take to achieve a specific outcome. It emphasizes control flow and changes to program states. Common imperative languages include C, C++, Java, and Python. Declarative programming, on the other hand, focuses on what the program should accomplish rather than how to achieve it. In this paradigm, you describe the desired outcome and the system or framework handles the execution details. Languages like SQL, HTML, Haskell, and Prolog are declarative in nature. Now, let's compare the key differences between two paradigms. Imperative programming requires you to specify how to perform each step, while declarative programming focuses on what needs to be done. In imperative programming, control flow and state changes are explicitly defined, whereas in declarative programming, these are abstracted away. Here's an example of imperative programming in Python. In this example, we explicitly define the steps to sum a list of numbers by iterating over each element and updating the total sum. This shows how imperative programming focuses on describing the sequence of operations required to achieve the result. Now let's look at an example of declarative programming in SQL. Here, instead of specifying how to iterate through the numbers, we simply ask the system to give us the sum of the numbers. The system decides how to compute the sum, allowing us to focus on what we need, not the implementing details. Imperative programming is ideal for tasks that require fine-grained control over the execution. It's commonly used in system-level programming, game development, and performance-critical applications where the programmer needs to control exactly how operations are performed. Declarative programming, on the other hand, is best suited for tasks that focus on outcomes rather than the process of achieving them. For example, database queries, web page markup, and logic-based tasks benefit from declarative programming. It abstracts away much of the complexity, making the code easier to maintain and understand. Some advantages of imperative programming include the ability to optimize performance and have fine-grained control over the system. However, these advantages come at a cost. Imperative code can become complex and harder to maintain, especially in large systems. Declarative programming offers a simple, more abstracted approach. It, it's easier to read and maintain since the focus is on the end goal rather than the process. However, this approach may lead to less control over the execution and in some cases can be less efficient for complex tasks. Many modern programming languages combine both paradigms to offer flexibility. For instance, in Python, we can write declarative SQL queries within the program, and In frameworks like React, we use declarative UI components but may write imperative logic to manage data and events. This hybrid approach allows us to get the best of both worlds. In conclusion, understanding the distinction between declarative and imperative programming is essential for choosing the right paradigm for a task. While imperative programming provides more control over execution, declarative programming allows for cleaner, more maintainable code. Modern languages often blend both paradigms to suit different needs. Thank you for your attention. Now I'd be happy to answer any questions you may have. Welcome to this presentation on memory management techniques. Today we will explore topics like stack versus heap allocation, memory leak detection, manual versus automatic garbage collection, and case studies comparing C++ and Java. Let's start with an overview of what we will cover in this session. We will dive into stack versus heap allocation, the techniques to detect memory leaks, the differences between manual and automatic garbage collection, and conclude with some case studies comparing C++ and Java. First, let's talk about stack memory. Stack memory is used for temporary storage of local variables and function calls. It follows a LIFO last in first out structure. The memory is automatically freed when variables go out of scope, but it has limitations. The most notable limitation is that it has a fixed size, and if that size exceeded, a stack overflow occurs. Next, we have heap memory, which is dynamically allocated at runtime. It allows more flexible memory management but comes with its own trade-offs. Memory is allocated manually, and if not properly deallocated, it can lead to memory fragmentation. Unlike stack memory, heap memory needs to be manually freed by the programmer, which can sometimes be error prone. Now let's look at memory leak detection. A memory leak occurs when memory that is no longer needed isn't freed, causing wasted memory and reducing system performance. Common causes include failure to deallocate dynamically allocated memory and circular references, especially in garbage collected languages. Tools like Valgrind, Address Sanitizer, and Static Code Analyzer can help detect and prevent memory leaks. Moving on to manual memory management, in languages like C and C++, the programmer is responsible for both allocating and deallocating memory. While this offers fine-grained control over memory, it also increases the risk of errors such as memory leaks and segmentation faults. Manual memory management requires careful tracking of every allocation and deallocation. On the other hand, automatic garbage collection, like in Java, takes over the task of memory deallocation, freeing up memory when objects are no longer in use. While this reduces the burden on the programmer and helps prevent memory leaks, it introduces some challenges such as performance overhead and potential pauses in program execution during collection cycles. Let's now look at C++, which uses manual memory management. Memory is allocated using new and freed with delete. However, if we forget to call delete, the allocated memory will not be released, resulting in a memory leak. Tools like Valgrind can detect these leaks using smart pointers like std unique ptr or std shared ptr is a safer approach as they automatically manage memory. Next, let's examine Java. In Java, the JVM handles memory management with automatic garbage collection. The garbage collector takes care of freeing memory when objects are no longer in use. However, there are different types of garbage collection, including minor GS for young objects and major GS for older objects. With this, with this simplifies memory management. While this simplifies memory management, it can introduce performance overhead, especially in memory-intensive applications. Now let's talk about some best practices for memory management. In manual memory management, it's crucial to always free dynamically allocated memory using delete or equivalent functions. Smart pointers in C++ help reduce the risk of memory leaks. RAII resource acquisition is initialization is another important principle, ensuring that resources are automatically cleaned up when they go out of scope. For automatic garbage collection, best practices include minimizing object creation in critical loops to reduce GC impact and using weak references to avoid unnecessary retention of objects. Optimizing memory use in long-running applications will also help improve performance and reduce garbage collection cycles. In conclusion, manual memory management provides control but comes with the risk of errors like memory leaks. On the other hand, automatic garbage collections simplifies memory management but at the cost of performance overhead. Regardless of the approach, tools and best practices can help optimize memory management and reduce potential issues. Thank you for your attention. Welcome to today's lesson on abstraction in programming languages. In this presentation, we will cover data abstraction, function abstraction, encapsulation, and polymorphism, all of which are essential concepts in object-oriented programming. Let's start with an overview of abstraction. Abstraction is the process of simplifying complex systems by focusing on the essential details while hiding unnecessary information. The main goal of abstraction is to reduce complexity, making it easier to understand and work with software systems. Data abstraction is about hiding the implementation details of data structures and exposing only the necessary aspects. For instance, in C++, we can use abstract classes to define a common interface for different data types, while the underlying details remain hidden. This allows us to interact with objects in a simplified manner without needing to understand the internal workings. Function abstraction follows a similar principle but focuses on functions or methods. We hide the complexity of the function's implementation, presenting only the interface that users need to interact with. For example, Python's built-in sum function allows us to add numbers without worrying about how the function processes them internally. Encapsulation is the practice of bundling data and methods that operate on that data into a single unit or class. This not only improves organization but also restricts access to the data, preventing unintended manipulation. In Java, we achieve this by making data fields private and providing public methods to access and modify them, ensuring that data is accessed in a controlled manner. Information hiding is an integral part of encapsulation. It involves restricting access to certain details of an object and only exposing the necessary parts. For example, in Java, we make fields private and provide public getter and setter methods, which ensures that external code cannot directly alter the object's internal state. Polymorphism in object-oriented programming allows objects of different types to respond to the same method call in their own unique way. This makes our code more flexible and reusable. Polymorphism comes in two forms: method overloading, where multiple methods share the same name but differ in parameters, and method overriding, where a subclass provides its own version of a method defined in the superclass. Abstraction and polymorphism go hand in hand in object-oriented programming. Abstraction hides the implementation details, while polymorphism allows different objects to respond to the same interface in different ways. This combination makes our code more adaptable and maintainable. We, as we can add new objects or modify existing ones without changing the interface that other parts of the system rely on. Now let's look at the key benefits of abstraction. First, it simplifies the design by hiding unnecessary details. It also makes our code more maintainable as internal changes don't affect the user interface. Abstraction promotes code reusability, allowing us to use common operations across different parts of our system, and increases flexibility by enabling us to evolve the system without breaking existing functionality. To summarize, abstraction helps manage complexity by hiding irrelevant details and focusing on the essential. Data and function abstraction simplify the way we handle data and operations, while encapsulation protects data. Polymorphism makes our code more flexible and reusable, and all these concepts are fundamental in object-oriented programming, leading to modular, maintainable systems. That concludes the presentation. Do you have any questions, or would you like further clarification on any of the concepts we discussed today? Hello and welcome to the presentation on error handling mechanisms in programming. In this session, we will explore types of errors, exceptions, and how error recovery works in programming languages like Java, Python, and C++. Let's dive in. Error handling is a crucial aspect of any programming language. It allows developers to anticipate and manage issues that may arise during the execution of their code. In this presentation, we will focus on different types of errors, how exceptions are handled, and how to propagate and recover from errors. We will look at examples in Java, Python, and C++. Errors can be categorized into three main types: syntax errors, runtime errors, and logical errors. Syntax errors occur when the code does not follow the correct language rules, such as missing semicolons or misspelled keywords. These errors prevent the program from compiling. Runtime errors occur during the program's execution, like division by zero or null pointer exceptions. These errors cause the program to crash if not handled properly. Finally, logical errors do not stop the program but result in incorrect behavior, like producing wrong output due to a flawed algorithm or condition. Exceptions are used to handle runtime errors in a more structured way. When an error occurs, an exception is thrown and the program can catch it and respond appropriately. In Java, for example, we would use a try-catch block to catch exceptions. The try-catch, the try block contains the code that may cause an exception, and the catch block handles it. This ensures that your program continues running smoothly even if an error occurs. Sometimes you need to ensure that certain code is executed regardless of whether an exception occurs or not. This is where the finally block comes in. It is used for cleanup actions like closing files or releasing resources. Even if an exception is thrown, the finally block will execute ensuring proper resource management. In some cases, you may want to handle different types of exceptions in one block. You can do this by catching multiple exceptions using separate except clauses or a single except clause with multiple exception types. This approach makes your error handling more concise and organized. Error propagation refers to how an exception moves up the call stack when it is not caught at the current level. It continues to propagate until it is either caught or reaches the top of the stack, causing the program to terminate. Error recovery is a mechanism through which the program can continue running after an error. This can involve retrying operations, using fallback strategies, or presenting meaningful error messages to the user. Let's look at an example in Java. If we try to open a file that does not exist, a file not found exception will be thrown. We handle this by using a try catch block. In the catch block, we can print a message to inform the user that about the missing file, ensuring the program does not crash. In Python, error handling is very similar. We can catch exceptions like value error or zero division error using multiple except blocks. This allows us to handle different types of exceptions in a structured way, making our code more resilient to errors. In C++, exception handling works with try-catch blocks as well. If an error is encountered, such as trying to divide by 0, an exception can be thrown. We catch the exception in the catch block and display an appropriate message to the user. This prevents the program from crashing unexpectedly. In conclusion, error handling is an essential practice in software development. It not only helps catch and fix errors, but also ensures that your application runs smoothly even when something goes wrong. By using exceptions, try-catch blocks, and other mechanisms, developers can create more robust and user-friendly applications. Thank you for your attention. Now I would like to open the floor for any questions you might have. Feel free to ask anything about error handling, exceptions, or any of the concepts discussed today. Welcome to this presentation on concurrency and parallelism in programming languages. Today we will explore the concepts of concurrency, threads, processes, and how different programming languages implement these principles. Let's dive in. Concurrency refers to the ability of a program to manage multiple tasks at the same time, even though they might not be executed simultaneously. The key benefit of concurrency is resource management. For example, handling multiple file downloads concurrently increases efficiency and responsiveness in applications. Let's start with the distinction between threads and processes. A thread is the smallest unit of execution within a process. Threads within the same process share memory space and resources. In Java, we can create a thread using the thread class and start it with the start method. On the other hand, a process is an independent unit of execution with its own memory space. In C++, we can create a process using the fork function. Unlike threads, processes do not share memory, making them more isolated but heavier on system resources. So, what's the key difference between threads and processes? Threads share memory and resources, which allows for faster context switching. Processes, however, have their own independent memory space, making them more resource intensive. Threads are ideal for lightweight tasks, while processes are best suited for tasks that require isolation. Java supports concurrency through its built-in multithreading capabilities. The thread class and the runnable interface allow us to create threads. We can override the run method in the thread class to define the task and then start the thread with the class method. Java also provides thread synchronization mechanisms, ensuring that shared resources are accessed safely. The synchronize keyword helps to prevent race conditions, ensuring only one thread accesses a resource at a time. In Go, concurrency is built into the language using Go routines. A Go routine is a lightweight thread managed by the Go runtime. Go routines are created using the Go keyword and they can be executed concurrently with other tasks. Go also uses channels for synchronization and communication between coroutines. Channels also allow Go routines to send and receive data safely, making it easier to coordinate and synchronize concurrent tasks. Synchronization ensures that multiple threads or processes access shared resources without conflicts. This can be done using mechanisms like locks. In Python, for example, we can use the threading lock to ensure that only one thread modifies a resource at a time. Deadlock occurs when two or more threads or processes are waiting for each other to release resources, creating a standstill. This can be avoided through careful resource allocation strategies or using timeouts to prevent indefinite waiting. Parallelism refers to executing multiple tasks simultaneously, often used often using multiple processors or cores. This is particularly useful for computationally intense tasks as it reduces execution time by dividing the workload across multiple units. While concurrency involves logically managing multiple tasks, parallelism focuses on performing tasks simultaneously. Concurrency handles tasks in a way that might appear to be happening at the same time, but not necessarily. Parallelism, on the other hand, executes tasks at the same time on separate processors. In Python, we can implement concurrency using the asyncio library. This allows us to define tasks that can run concurrently by utilizing asynchronous programming. For example, we can run multiple tasks concurrently with the await keyword, managing their execution efficiently. To achieve parallelism in Python, we can use the multiprocessing library. This allows us to run tasks in parallel on different CPU cores, making it ideal for CPU-bound tasks. Each process runs independently with its own memory space, improving performance for heavy computations. To sum up, both concurrency and parallelism are crucial concepts for developing efficient applications. Concurrency helps in managing multiple tasks, while parallelism speeds up computationally heavy operations. Understanding these concepts and how they are implemented in different programming languages will help you optimize your code. That concludes the presentation on concurrency and parallelism. Thank you for your attention. If you have any questions or need further clarification, feel free to ask. Welcome to day 20 of our programming languages series. Today we will dive into the implementation of programming languages covering essential phases like lexical analysis, parsing, and code generation. We will also explore the differences between compilers and interpreters and learn how just-in-time compilation works. Let's start with lexical analysis, the first phase of language implementation. This step breaks down the source code into meaningful units called tokens. These tokens include keywords, operators, and identifiers. Lexical analyzers such as lex or flex are used to perform this task, ensuring that the code is ready for the next phase. After lexical analysis, we move on to parsing. Here the tokens are arranged in a structured format like a parse tree or an abstract syntax tree or AST. Parsing ensures that the sequence of tokens follows the grammar rules of the language, setting the foundation for further analysis and code generation. Once parsing is completed, we proceed to semantic analysis. This phase checks for logical errors such as type mismatch or improper use of variables. The code is then ready for code generation, where it is transformed into machine or intermediate code. The code generation process turns the structured representation into executable code. Now let's compare compilers and interpreters. A compiler translates the entire source code into machine code at once, generating an executable file. Like languages like C and C++ uses compiler. On the other hand, an interpreter processes the code line by line, executing it immediately. Examples of interpreted languages include Python and Ruby. Compilers are known for their speed. Once the code is compiled, it runs faster than interpreted code because it has been converted to machine code ahead of time. Additionally, compilers can optimize the code for better performance. However, they do require time to compile the source code before execution. On the flip side, compilers have some drawbacks. The main disadvantage is the long compilation time, especially for large code bases. Additionally, compiled code must be recompiled for each platform, limiting probability. Interpreters, by contrast, don't require a separate compilation phase. Code is executed line by line directly from the source. This gives interpreters flexibility and debugging is easier since you can track errors as they occur. However, interpreters generally have slower execution speeds due to the line by line translation. While interpreters offer flexibility, they also have significant downsides. The primary issue is slower execution speed, as the code must be interpreted each time it runs. Moreover, because there's no separate executable, the source code must be present to execute the program. Now let's talk about just-in-time JIT compilation. JIT compilation combines the best of both worlds. The code is compiled during runtime, allowing for optimizations based on how the code is actually being used. Java is a prime example of a language that uses JIT. The code is first compiled into bytecode and then optimized and executed by the Java Virtual Machine or JVM. In practice, different languages implement these strategies in various ways. For example, Java uses JIT compilation, while Python is interpreted but also utilizes bytecode for performance. C++ is typically compiled directly into machine code. Understanding these implementation strategies can help you choose the right language for your needs. Why does all this matter? Language implementation strategies directly affect performance, debugging, and portability. Compiled languages tend to offer faster execution but may be less flexible, while interpreted languages are easier to debug but slower. Understanding these differences can help you choose the best language for your project. To recap, Language implementation involves several phases: lexical analysis, parsing, semantic analysis, and code generation. Understanding how compilers and interpreters work helps in choosing the right language for specific tasks. JIT compilation offers a balance of speed and flexibility, and different languages implement these strategies in various ways. Welcome to the presentation on runtime systems. Today we will explore concepts such as stack and heap management, virtual machines like JVM and CLR, and garbage collection strategies. Let's dive in. Here's the agenda for today's session. We will start by discussing stack and heap management, followed by virtual machines, specifically the JVM and CLR. Finally, we will look at garbage collection strategies and their importance in memory management. First, let's talk about stack and heap management. The stack is used to store local variables, function parameters, and return addresses. It operates on a last in first out or LIFO principle, meaning the most recently used items are processed first. It's fast and automatically managed by limited in size. On the other hand, the heap is used for dynamic memory allocation, and memory is managed at runtime. It provides more flexibility but can introduce overhead due to the need for manual or automatic memory management, depending on the programming language. Let's take a look at some examples. For the stack, when a function is called, its local variables and parameters are pushed onto the stack. When the function finishes, the stack is popped, removing those items. In the heap, we have dynamic memory allocation. For example, in C++, we use the new and delete operators, while in Java, the new keyword allocates memory on the heap, and garbage collection handles memory management. Now let's explore virtual machines, starting with the Java Virtual Machine or JVM. The JVM abstracts the underlying hardware and operating system, providing a consistent environment for running Java programs. It executes bytecode and performs just-in-time compilation, converting bytecode into machine code at runtime. The Common Language Runtime or CLR is part of .NET Framework. It manages the execution of .NET programs, supports cheat compilation, and provides garbage collection, ensuring efficient memory management. The JVM has several key components. The class loader loads class files into the JVM at runtime. The bytecode interpreter executes Java bytecode, ensuring cross-platform compatibility, and the garbage collector automatically reclaims memory, preventing memory leaks by cleaning up unused objects. Similarly, the CLR provides key features for .NET applications. It handles garbage collection, automatically reclaiming unused memory. It also compiles Common Intermediate Language or CIL into machine code through JIT compilation. Additionally, the CLR enables interoperability with unmanaged code such as calling C or C++ libraries from managed code. Garbage collection is a crucial part of memory management. It automatically reclaims memory that is no longer in use, helping prevent memory leaks and improving